Hi, I'm Mark Wilson, the Engineering Heretic, and today I want to talk about moulded components and what goes into moulded components. Of course, I'm a toolmaker. I worked in the plastic injection moulding industry for about 25 years, so I am somewhat of an expert on the subject of injection moulding. And we have a number of moulded parts on my desk here, but I'll just talk about them one by one and explain what's involved and why do we injection mold. And the main reason we injection mold is because it really produces like a part like this. It's a molded part for, I forget what for, but we'll talk about that in a minute. But this particular part here, in a mold, and I believe it would probably be a 2-cavity mold, would make 2 of these every 30 seconds. You may want to argue, well, why with in this day and age where we can 3D print something, why don't we just 3D print? And the reason is, if you build a mold for that, which is rather expensive, it will produce 2 parts every 30 seconds. That's 1 every 15 seconds. If you try to 3D print that particular part, it would take probably the best part of an hour and a half, and you'd only have 1 part every hour and a half. So clearly that's not going to satisfy a production situation where you're going to make like cars, you're making maybe 600 a day or something like that. We want thousands a day. Clearly a 3D printer is not going to make that up. In the injection molding industry, we do use 3D printing, but mostly for confirming whether or not a part is serviceable, to test a part before you actually build a mold, and to sometimes go for concept things and stuff like that. But let's just discuss a few things about injection molds and a few rules about things in injection molds. Firstly, in an injection mold, you must have what we call a top half and a bottom half. Sometimes the top half of the mold, or the mold runs sideways in the machine, so the part just drops out freely. But we need what we call a cavity and a core. And normally the cavity is in the side of the mold that is on the, if you're standing in front of the machine on the right hand side, that would be called the cavity or the fixed side of the mold, because this part of the mold here does not move, and the other part of the mold does move. I call this it's often called the fixed side of the tool and the moving side. Now on the fixed side of the tool, there is in this case here, there is the part that goes into the fixed side of the tool is this section here, and this has a very simple split line, this particular part. It is just a flat face. The split line is this edge around here. That face there is the split line. This face here is also on the split line, and that face there and this face here are in exactly the same line. That's the split line of the tool. In this case here, it's very, very simple. Now, an injection mold also needs a track in order to get the plastic to the mold side, or the cavity in this case. And so there's the reason why this is a 2-cavity mold. I believe the gate is on. There's a little bit of a blemish here. That particular blemish is where the gate is, and that's from a gate that is a tapered hole from the shut face, or this face here, a track along the mold itself, usually round, and then disappearing into a tapered hole that starts from maybe around about 6 to 8 mil diameter, down to about a 1.5 mil diameter here where the gate is. And this is what we call an automatic gate. Is that because this runs down this tapered hole here, it will, as the mold ejects, or the part is ejected from this, it will snap off the gate on the ejection process. I'll talk about the ejection process in a minute. So we have a delivery method that gets the plastic to the cavity. We have, and that's on the fixed side, because generally the RAM of the machine and everything like the RAM where the plastic is heated up into it's like a meat mincer sort of thing, which basically screws the plastic up and then forces the plastic into down with a plunger arrangement into a runner system. In this case here, it's a cold runner system along the track, which freezes off and down this little hole here and fills that part there. That's the fix side. We also need a system to regulate the temperature of this mold, because if this was just left to its own devices, every shot would warm the mold up more and more, and that would change the ability for the mold to work properly. So we need a cooling system. Usually it's water. Sometimes it's actually warmed up a little bit, but quite often it's we just call it cooling. Sometimes even we want to run mold rather hot, hotter than say near boiling point. We'll actually run hot oil to regulate the temperature of the mold, but we call it cooling because that's just the typical term we use. So if I use the term cooling, I just mean the water circulating through the block, usually through a bunch of drilled holes in the insert. There's an insert on this side of the tool in a big bolster, and an insert on this side of the tool, and that's normally heat treated and to around about 52 Rockwell C. So we need a system to get the plastic in, a system to cool both on the moving side and the fixed side, and also we need a system for ejecting the part or getting the part out of the mold. Now this one here is relatively obvious. You look at the part itself, we're looking for little round, little circle things. Not really obvious on this one. There's a couple of little date things, but we're not worried about that. This part is ejected by these areas here. Now this is called a sleeve ejector. Now essentially there's a core pin that runs all the way to the back of the moving half of the mold, all the way to the back of the die block on the back plate, and that core pin remains fixed. And around that there's a subsequent moving plate. So as the mold comes apart that way, there is a movable plate with these pins or ejectors. In this case here we call them sleeve ejectors because they go around the core pin and they move forward as the mold opens up. This part will stay stuck to this side of the tool because that's the biggest surface area. That will just lift out of the fixed side of the mold, be stuck on the moving side of the mold, and then this plate will, with these core pins stationary, this plate will move forward and pop out this part. And of course it just lands under gravity, usually in a box or a conveyor belt. That's a simple mold, mostly likely a two cavity. Let's look at something a little bit more complicated and we'll see some of the differences. I have here just a container from my kitchen, and this one here is this is ABS plastic. This one here is a different plastic. This is high clarity polyethylene, I believe. And this one here, of course, we have the fixed side of the tool on this side. This time we have quite a pronounced core reaching up on the moving side of the tool on that side. And also we have a delivery method, but this is a little bit different. If I put my finger on the back of this here, there's a little bit of a blemish right there, which you see on most parts. I pointed out the blemish on this particular one here. This blemish is in the center here, and of course that requires a runner system that runs from the back of the mold here, and the plastic is heated all the way right to the cavity. Okay, so this time here, when this one ejects, it will also eject with the runner system, will also be cooled off, and that will land in the bottom on the conveyor. This one here, it's just the component itself, because the plastic is pumped directly into the mold through this little blemish here and fills the cavity, and of course that cools off. And when this die separates, there is a split line here. This one here, like this one, is just a standard flat split line. And if I put my finger here, you can just feel a little bit of an edge on this section here. And where that little edge is, you can run your fingernail over. There's a slight little radius that side. So about halfway in the middle of that little flange there, there's a little split line there. So this will split in this direction here. This will stay stuck on the core. And this part here, of course, so the whole thing will move back in that direction there and separate. And this will be stuck on this particular core. But there's another problem with this particular part. There's a thread here, and if I go to eject that part, we can't get this thread out without something moving away here to let that go. And if you look very closely, there's a very, very slight little crease here, a little line here, and on the opposite side, there's another one. And that's because this particular part has what we call sliding cores. There's a section, as the mould opens up, there's a sliding section that slides out of the way in this direction, and that one sliding out of the way in that direction. And that mostly will likely need its own cooling system. So now, with these two sections slid out of the way, we now can eject this part by, in this case here, there's, I believe, it's probably a stripper plate mechanism. So there's this whole section from here. You can feel a little bit of a crease line there where that core has come away. There's a little bit of a crease line here. Then this here, this section here, there's a little, this whole plate, there's a whole section, the core will remain stationary. And the whole outside of this whole there's a moving section here, will push this forward, and this whole section will move forward, pushing the moulding off the core. As that's doing that, we have another problem. We have atmospheric pressure as well. So we have, 14.5 psi, pounds per square inch. That's a very big area inside there that will be sucking onto that. So if you try and push that out without pumping some air in here, you will most likely turn this thing inside out and it won't come off. It'll just sort of smash itself on the way out. So we need another way, another method for popping, or there's, you can feel in the back here, there's a section, you can just feel a little bit of a ring on this side, a little bit of a ring in there. And there's a little pin that pops forward a little bit and pumps compressed air in as this part is stripped off the mould. And of course then the part will just land in the bottom of the machine, just like any other part. So that's that particular part. Of course, this will need to run a lot faster than anything like this, because this is a car component. This one here, they're making thousands of these a day, so that will run quite quick, probably around about a 15-second cycle or something like that. That's that one. Let's look at the lid and see how that changes. This one here, like its container, once again has a core reaching up in here. It has a method of delivery. There's a little blemish I can feel there. And so it's a hot runner system. The core reaches up in here. The split line is now at around about that. I can just feel a little bit of an edge there. It's a flat split line, just a dead flat face. And this time, when the mould separates, and of course I should have mentioned before, all mouldings have a thing called draft on them. There is a slight taper on everything here. If you measure that there and the bottom here, it will be slightly narrower. These ribs here will be slightly wider at the top as they are at the bottom. Those core pins will have a slight taper, and they go all the way through to the, no, there's other core pins from the other side, but they have a slight taper on them. We call this draft, and that allows the component to come out of the mould when it's being ejected or even being opened. So there's a slight taper. Usually, I think on that case here, it would probably be something like about 2 degrees. Here, probably something like about the same. But this time we have another problem. We have a thread on the inside here. So if we try to strip this part off directly, it's not going to come off because we'll rip this thread off on the way out. So what this mould has is a rotating section that actually unscrews out of the way. We'll leave this part sitting on just this little edge here inside on the cavity with this part screwed back out of the way. And there's a mechanism, a hydraulic mechanism for unscrewing this. And then what will happen, there will be a plate that strips this off the core. It'll be just sitting there anyway, and it will most likely just fall into the machine. There may be even a compressed air method for just popping that off at the end there to get this part off. So that's containers like that. Now let's look at something a little bit more complicated and more of an automotive component. Let's look at this part here. This component here is a light box. There's a little light will go in here for an instrument cluster on a car. So in an instrument cluster, there's this little thing here that takes a little light there that throws the light forward here. And there's a couple of other rules about moulds. If you look at that in that direction, directly down this direction here, anything that you can see on that projected area in that direction must come from this half of the mould. If you flip this over, anything you see from there must come from that half of the mould. So that makes a bit of a dilemma here, because we can see the bottom of that edge there, but we can't see that from the top. But we can see this clip area here from the top of the mould, or the fixed side of the mould, but we can't see that from this side. So there's something going on with what we call the split line here. This is a complicated split line. And so let's track this split line and see what it does. This one here, of course, that's relatively simple. We have a split line that runs on the main face here, runs up this area here, across there, and then back down again. So there's a section on the what we call the moving side of the tool that reaches up to this point here and across here, and then back down again in order to get that cutout. Then we're back on this face again here, making our way around to here, and then we see something a little bit different. There's a split line that runs up on the angle here to that point there, and then goes across here to that section. Where does it go? Runs across here, right across here, and then back down again. And there's something that reaches up inside of that again, something that reaches up inside here. And I think there's it's a split thing. This is a bit complicated, so there's a couple of funny things here. And in order to get this section here on this half of the mould, and that section here on that half of the mould. So this split line is doing all sorts of crazy things. And then we see the split line coming back down here, back to the main face again. Of course, we get to the other side here. We're doing the same little cutout area that this one's here is. Back down again, back, round here, back up there, across to the top then, there. Then we have this little clip here, and so our split line runs, where does it run? It runs, I believe, up this edge. Yeah, I can feel a little bit of a crease line there. Up this edge here to that section there, runs across. No, I don't think that runs in the other direction. No, it actually comes right across here, up to there. We've got this clip here, comes up that section there, across here, then back down again. and so on and so forth, working its way around. So quite a complicated split line on this particular part. This is a 2-cavity mould, and there's a small little blemish here where the subgate, which is in a cold runner system, gates that part there. That's a little bit more complicated. Let's look at something a little bit different again. Now this particular mould here, this is a Robert Bosch component. It's got a cover and a base. It goes together like that, clips together. It's for a little a box for some computer or some electronic stuff. It's probably for a car. And this one I built back in the 90s. This one here is what we call a family tool. It has this particular base and this particular cover in the same mould. And they're very similar sort of sizing, things like that, so that the moulding is not too imbalanced. It has a delivery system here where the plastic is, in this case here, it's called the 3-plate tool, and I won't bore you with the complications of 3-plate tools, but assuming it's a bit like the hot runner system for this, but it is a cold runner system, but it injects, and there's a removal system at the back of this here that gets this cold runner out. But this was a 2-cavity family tool that made a cover and a base in one go. And the gating is in the centre here, and of course in the centre there. Remember the rule: whatever is on this side of the tool, whatever you can see, must come from, in this case here, the fixed side of the tool, and whatever you see on this side of the tool must come from the moving side of the tool. And this one here, you can see the ejector marks here. There's these little round little circles here where the part is ejected, and this part here pushes between these points here. There's 2 pins there, and there's 2 pins there, and the same on the other side. And I believe that is all the ejection this part has. I believe so. Yeah, that's all that has. The other one's a little bit different. We'll talk about that in a minute. So this time here, remember the rule. So we have this little clip here must come from this half of the mould, but the split line is, the standard split line is this one here, this edge here. There's a slight angle, a little chamfer that goes down in that direction there. So we need to get from this side of the tool up to the split line, which is now here, run across that edge there, and then we come up even higher again to, I believe it's, there's a small radius there. It runs right up to this edge here. Is it? No, it's a sharp edge there. Runs right up to the top here, runs around there, and then back down again. Does the same thing here. And of course, like the other opening we had before, we have a split line that runs along here, up and around here, and down again as well. So that's a reasonably complicated split line. Now we also have clips inside here. There's little clips there. Now we've got a little thing reaching from the fixed side of the tool, reaching into the core of the cavity side of the tool. So you see this little window here made specifically to reach through to get to the other side, because that bottom of that clip there must come from this side of the tool. And that is that particular component. This one here, this component here is in the family tool here. We have an ejector pin that is there, and there, there, and there. But we also have a couple of other problems with this particular mould. These pins, these prongs here, are very, very long and skinny, and there is no way you'd be able to build a mould and get that out of the mould, because that comes purely from the fixed side of the, from the moving side of the tool. And also you have a lot of problem with air being trapped as this plastic was being forced down in here if that was just a blind hole in the mould. So what I did when I built this tool was I attached this section here to a square ejector, like those pins there, coming from the ejection system. So what would happen is, as the ejection system would move forward and pop the part off, these sections here would also lift forward, allowing this part to fall off. So we've done a little bit of a thing there to get that part filled and also to be able to remove it, because that would be just a blind hole in steel. The split line on this particular part, remember the rule, we must reach the bottom of this edge here from this side of the tool. So the split line here runs flat across here, around here, directly across the start of that radius there to the bottom of that edge there, back down again, and then it follows this around all the way around here, back up across to the top of that, down and around there, and so on and so forth, reaching, going all the way around. So each one of these clips here, it jumps up, runs across here, then back down again to this face here, and so on. And of course this opening here, it runs up here, just jumps up a bit across there, and runs down here and around there, and so on and so forth. And that's how this part is moulded. Let's look at something a little bit more complicated and require a considerable amount of effort to build. Let's look at this part here. This is a Toyota Camry high mount stop lamp. Goes in the back windscreen of a mid-90s Camry. I built this mould as well. Let's look at how it's filled first. First of all, there is a telltale little thing here that needs to be cut off. I've left it on here, where the plastic was heated at the back on the fixed side of the tool. It was heated on a center. This is a single cavity mould. Runs across here, heated all the way to the die face, and then it runs across a cold runner system to a subgate, which is basically part of an ejector pin. You'll see a little ring here where I can feel it right here. There's a little ejector pin there. This one here has half of the pin cut away, and the subgate would run into that point there, fill this whole cavity from that point there, whole thing there, and then that's popped out with the ejection system on the way out. And this would be trimmed off later on. This has a number of issues in this particular mould that need to be looked at as well. First of all, the split line runs all the way around this edge here. That's sharp on that edge there, all the way around here. So the split line runs all the way around here, that edge there. So the whole face of the die is following that contour. And then, of course, that's a relatively straightforward thing. But on the other side, we have another problem. We have a section here that you cannot see from this side of the tool or from that side. In other words, that section there. And to get that out, if you look around here, you'll also see a secondary split line of a section sliding out in this direction here called the sliding core, just like the thread situation here. In this case here, this is on the bottom of the mould. This whole section on opening would slide back out of the way, and that of course needed to be cooled. So there's one section coming out there. So that leaves this part here with that section gone away, free to come out, except for the fact that we have also a whole number of other things here. Remember the rule? What you can't see, we can't, this edge underneath here, these edges underneath here, they would not come out of the mould. This whole section would not come out of the mould. And this section here, which is buried underneath that point there, that would not come out either, nor would this little clip here. So attached to the ejection system, there is, if you see, look very carefully here, you'll feel a little bit of a crease line of this section here. There's a square section here. There's another section here that I can see as well, and another one there. And there's also another line that runs across here, down there, and across there, up and around here. And so what that is there's a whole section that as this part ejects, there are some pins, there's some core pins on here, on some ejector pins here, ejecting the part. But attached to that plate, there's a whole section that lifts out of the mould on an angle in that direction. So as this part goes to eject, these sections here will basically lift out of the way in that direction there. This one will go in that direction. As it comes forward, it will travel on an angle. And the same thing with this section here. This will travel on a slighter angle because it doesn't have to move as far. And also, underneath, there's also another section that slides out in that direction. And so as this part ejects, these sections here are going forward with the component and sliding into the center. So that part will then be free to fall out of the machine. And all these parts needed to be cooled. That was quite a complicated mould. And that's basically the how these things are moulded. And of course all these parts, this part here, it's a single cavity. Every 30 seconds you'd end up with a part. You could not do that with a 3D printer. Quite an expensive mould actually. In fact, all moulds are quite expensive. I think I spent probably around about 10 weeks working on it. It was a team of people, but mostly myself, but there were a team of people doing things. Probably about 10 weeks to build that mould. It is a through-hardened inserted mould on both sides. It has a sliding core. We call them lifting cores, angular lifting cores. And also on this, the texture is an acid etched texture on the sliding core as well as the fixed side of the tool to give it a texture. As is these parts here, they have an acid etch on them so that to make that mottled look a bit like that. All parts need, and these parts here, this one here needs a very high polish on there. It's usually a hand-worked diamond polished finish. It looks like it's been chrome plated, but it's actually the steel. Expensive to produce. These parts here on the bottom side, it doesn't matter that much because you're looking on the underside there, but on the top side there where you do see it, of course you can't see any of the blemishes. There is a slight little crease line around here where the sliding core came away, but that's all you can see. So it just looks quite normal in the car, but there's a lot going on underneath it. And that's injection moulds. They're very complicated things. To build a car, there's a number of components, probably closer to maybe 500 moulded components on a car. All of them have to be produced by tool makers. That one there, back in the day, I think it was something like about $50,000 back in the 90s or something like that. These ones here, probably closer to about $25,000. A lot of money. These days here, most things are made in China or Asia somewhere. They're still making moulds exactly the same way as we made them in Australia, except that they're making it, of course, at the lower standard of living. They can make these moulds. We can't in Australia, but we still have moulded parts sent here. We have moulds being built, sent to Australia and moulded here as well. So that's injection moulds, and if you're looking at a part, it's just as a tool maker you end up obsessively looking at things and how did they do the split line and things like that. How do they go about moulding things? But that's basically a little bit of information about how injection moulding parts are produced. And I'm Mark Wilson, and thanks for watching.